So let's get started, everyone. So welcome back. You're enjoying the spring weather, at least until the weekend again. So today we're going to talk about matrix sketching. It's going to kind of be in two units. We've talked about first the dimensionality reduction, and also kind of the streaming or large scale algorithms So we're basically going to look at how do you do dimensionality reduction at these extremely large scales. So in the plan is to kind of go through 3 or 4 or 5 different algorithms that kind of give you a variety of, depending on the scenario of how big the different dimensions are, I'll kind of give you guidance on what I think are the right way to do it. It's an area, it took me like 10 years to really understand this area. So hopefully you guys will understand it after like just one lecture, but so probably not everything about it, but hopefully I picked out the key pieces and lessons here. Okay, let's see, where are we? What's the news in the class? We're in the middle of dimensionality reduction. We've only got like 8 lectures left. What is that? So it's so we're getting towards the end of the semester. The dimensionality reduction homework is out and posted. I felt like the last week or so for you all in this class was pretty hectic. It was hectic for me too. Meeting with all of you, it was great. I enjoyed that. But the dimensional reduction homework is probably, in retrospect, after I posted it and slept on it, but it's already up there. It's probably like simpler and easier than like it needs to be. But I just kind of forcing you to walk through the differences between SPD and PCA, learn how to project these in 2 dimensions, and look at multi-dimensional scaling, which we'll talk about in the distance metric learning part of the class. So if you want something more challenging, let me know. I think I see how to maybe ask a more interesting but question that would take you a little bit longer. I'm happy to change the homework, or we can leave it as is. So who'd like to see a little bit harder homework? Okay. Yeah. Okay. Just a few votes. So okay, I'll probably leave it as is. Maybe I'll add an extra bonus question. So there's a bonus question on here about using some of this like matrix sketching stuff. Yeah, okay. I wanted to get the homework out, but it's probably a little isn't too hard. I want you all to be working on your projects. I think for the most part, the classes made a lot of good progress on the projects so far. So I'm pretty happy with the progress. You've got the next month to mostly focus on those. There's going to be another homework on graphs, and I could easily have the homework due on this date before the end term. So you do it before you do the end term test, or I'm happy to have it due on this. This is like the last day after classes end. Or I could have it due somewhere in between. Do you have any preferences? Do you like where it is now or earlier? So who wants it where it's due now? And who would rather have it due earlier? Okay, so maybe I will try and have it out earlier so you can do it. It'll be almost impossible to get graded before the interim test with we can't really start grading until the late assignments are in. So I'll try to have it out earlier, and then you can do it. So it'd be feasible to do it before the interim test. So I'll try and do that. There was some flexibility in there. You also be working on your final report and your poster outline around them. So it'll be like a busy time as well in the course. Okay, great. So that's where we are. All right, so matrix sketching. Okay, so let's quickly review of our input. A, we're going to think of as an element of our n by d. That means we can think of the rows as A1, A2, up to AN, and these are each, this is a subset of RD. So these are points in RD, each row is a point in RD, right? And we thought of thinking about this as a matrix A with n rows and d columns. And kind of the right thing to think about here is the SVD of this. So if we do the SVD, then we can decompose this into a large orthogonal matrix U, which is n by n, a diagonal matrix S. And so it's only stuff on the diagonal. If we want to multiply them together, you need to pad it with zeros at the bottom. And then you have another orthogonal matrix transpose, V transpose here, right? And so now review the columns of U. Okay, so this is a left singular vector. We'll call it uj. The value here, sjj, sigma j, is going to be the singular value. And then the row of V transpose, which would be the column of V, is going to be, this is the right singular vector. This is Vj, this is an Rd, and Uj is an Rn. These are n-dimensional vectors here. Okay, and so I have the property that I can write A as the sum of j equals 1 to d. In this case, we're writing d is less than n times uj sigma j vj transpose. The sigma is a scalar, uj and vj is an outer product when I multiply it, so it gives an n by d matrix scaled by the sigma j. Okay, and I can write A sub k, where I just sum this, instead of up to d, I sum this up to k, the same thing here. Sigma j vj transpose, right? The key here is that I've summed this only up to the kth term here, and this is kind of the best approximation. So if I write the arg min of b, where the rank of b is equal to k of a minus b, in either the 2 norm or the a minus b, or the Frobenius norm, this is going to be equal to a sub k in this form here, right? So if I want to find the matrix B, that's a best rank k approximation, meaning all the data lives on a k-dimensional subspace that best approximate A in these 2 ways. This is how you write it. The SVD gives you solution. Okay, and what is the spectrum of A minus AK? The spectral norm, or the 2 norm, A minus AK, the spectral norm, this is exactly going to be sigma k plus 1. Okay, So what is this measuring here? This is measuring, this is equal to max of x such that the norm of 1 of a minus ak times x. Okay, so I've taken this. Okay, it's a little bit smaller so you can read it. Max of a minus ak times x. So I've taken this a minus ak matrix here to get the 2 norm, and I've taken the max over all unit vectors. I've multiplied it by this term, and I'm getting the maximum norm. So in any direction, when I multiply by x, I multiply all the terms, all the columns, or sorry, all the rows in here, I dot them with x. This gives me a dot product. I add all these squared terms up, and then I take the square root. Okay, so that is equivalent to this. And so after I've subtracted out the first k terms here, what's left are the k plus 1 through the last terms. And the direction, which is largest, is the direction that this is true. The argmax is going to be v of k plus 1. It's the right singular vector, the k plus 1, the first one I haven't factored out. That's what the spectrum norm is. The Frobenius norm, okay, I can also write the Frobenius norm of let's say a minus a ak. The Frobenius norm, I'll just write squared, is just going to be the sum over j equals k plus 1 up to d of sigma j squared. So if I just take the norm of this, I would take the square root of this side and of the right side. So this is just all the max. Okay, so the best rank k approximation in a lot of ways is describing kind of the solution here. It encodes a lot of useful information. If I want to project onto 2D, tells me in some sense the best way to do this. Okay, it's a very useful tool to do, and kind of should be your first tool of your toolbox for dimensionality reduction in most cases. Okay, so the question is, if I want to compute this, how to compute? Okay, so how to compute the, well, let's say a sub k, right? So how do I compute the best rank k approximation? Okay. So how do you do it? If I were to tell you to go do it, you would do what? Would you implement it yourself? Would you? Yeah.
You call SVD to take the top K.
Yeah. So you'd call SVD. What does SVD do?
It breaks the matrix down into the right singular values, the right singular vectors.
Yeah. Okay. So it computes these 3 matrices probably, or depending, maybe you can skip some steps. You may not need to compute all of them even. But like when you call the SVD, what does the algorithm underneath the SVD do? Or not even the algorithm. It pretty much does not matter what language you use it in. You can do it in Python, in Python. If you do it in MATLAB, if you do it in one of the C languages. How to compute AK? You call SVD in your language, right? So and this goes and calls a library underneath here called LAPACK. Okay. In 2021, Jack Dungara, who came here to speak a few months ago, won the Turing Award. He is basically, was the lead architect and has been maintaining LAPACK for like 40, 50 years. Okay, this one library was written in Fortran, has been the underlied, every matrix library you call in any language will call an SVD operation in So a lot. It used to be when I was in school, you could call it through C, and Fortran can compile directly into C. Man, the documentation for the API was very hard to use. It's now much easier to call the SVD. But it calls the same language. It's super well optimized. It decides how big is your matrix. It does a little profiling, and it calls a number of different algorithms under the hood, depending on the situation. You maybe only want the top K, and then there's a different algorithm you can run to just call the top K. Okay, this had kind of been, it's written, I think, the 1970s, and it's kind of been unchanged for the most part until about 10 years ago. Okay, and there was some theory maybe starting about 15 years ago and starting to kind of change how we did this in practice for a very large scale about 10 years ago. And there's a new way to think about this. The challenge is, what is the runtime is going to be O of ND times the min of N times D. Okay, so you basically needed O of ND times the minimum of N and D time to call this. Okay, so it's if N and D are, if D is pretty small, it's not going to take too long, right? If N and D are both large, and we start to see some very large kind of machine learning, data mining training sets, large matrices, where N and D are both large, and you really want something a lot closer to linear time. When things grow quadratically in time, it starts to be painful. Again, this is really well optimized. So if you're, it's not so bad. Okay, but people said, well, we can maybe speed this up by like a factor of 10 in some cases if we're allowing a little bit of approximation. Okay, and these are numerical algorithms. So the tricky part about solving the SVD is typically it's getting up to 10, 12 digits of precision. It's often used in scientific computation, often in simulation, where you have to iteratively apply this over and over again, and a little bit of error can move on to the next round of the simulation. So it's important to get it highly accurate for a lot of cases. For machine learning data mining, we're okay with maybe 2 or 3 digits of precision. Okay, and it kind of changed the ballgame a little bit in how this worked. We can now think, how can we do this so better? All right, so I'm gonna say you can call the SVD as a black box. We'll take roughly, let's say, ND squared time, right? So let's think of O of N D squared, but we don't want to call it too often. Okay, and so then how do we compute this for very large scales? Okay, and I want to get it so it's kind of, let's first look at why, so how to get ND squared algorithm. And so we're going to again talk about streaming. Okay, and this is where you see data in order, and your storage space on your device, on your, say, in memory or on a router, is going to be less than kind of N times D. So I need space that's much less than N times D. Okay, the sort of space we'll be thinking about will, in fact, we'll be focusing on where N is greater than D, and I'll give you a few different scenarios, and it will change how to think about this. Okay, but the total space we have is much less than N times D. We might be able to have like D squared space. Doing that would be okay. So typically D squared is okay, but sometimes we want even less than D squared if D is really big. Okay, so we're going to be seeing A1, which is a row in RD, then A2, a row in RD, then A3, and so on. Each of these is D space. So I need to be able to at least get D dimensions. I want to get the top principal components, and maybe I can make another pass over to project it down, or I want to know the mode, the direction of the most variation, or the top few directions of most variation. Okay, so that's kind of the scenario we're looking at. Okay, so let's first look at the streaming algorithm, let's say the setting is where, let's say n is equal to 100 million, and d is equal to say 1, let's say 100 to 1,000, somewhere in this range. Okay, so now d squared is not too big. It could be big, but it's not inconceivably big to work with. Okay, so the first way of thinking about this will be so a summed covariance. Okay, and we're going to be thinking about, we're going to set a matrix C, which is going to be equal, which is d by d, and we're going to set each cji equals to 0. So we're going to set this as all zeros, and then we're going to have for ai for I equals 1 to n, right? We're going to stream over these values, okay? And what we're going to do is we're just going to set C equals to the old value of C plus equals AI transpose. Okay. Okay, and then what we would like to do is we're going to do at the end of this, we're going to do the eigen decomposition of C to get VL. And so we're going to say that VK are going to be the top K right singular vectors, and square root of L are going to be my singular value. So I'll call the eigen decomposition of C, right? And so at the end, so I just need to call this once at the end. C is now a D by D matrix, so this would take like D cubed time, but if D is less than N, so this used only D squared space. So the total space I used is the total space here. So this space is D squared. Okay, and so the reason why this works is so C at the end here is going to be equal to AA transpose at the end. One way of computing AA transpose is just looking at all of the rows of A and summing up and doing their outer product. So that means that the eigen decomposition of C is basically going to give me the SVD of A kind of squared, right? And we did this at the end of the lecture on Wednesday, where the eigen decomposition of A transpose is basically encodes the right singular vectors and the squared singular values as the eigenvalues. So once I have this, I can just read these off here. Okay, so this has no approximation, and this works well if D squared space is okay. So if I'm at 100 to 1,000 kind of dimensions, then, or even less than that, 10 dimensions, right? I want to get down to 2, this is pretty efficient. Okay. So I'd worked in this space for a while, and I didn't realize that this simple algorithm solved this case for, but this should be kind of the first thing in mind. If D is not too big, you just want to do this. There's no approximation. It's small space. You're just storing the covariance matrix by summing the outer products. Okay? Okay. If D is bigger, the next setting we want to think about, okay, again, we're going to have N equals something like 100 million. And D is now going to be equal to, let's say, 10K to 100K. And I don't want to store I don't want to store d squared. D squared is going to be too painful to store. Okay, so now d squared is too big, and I want to get like the top 2 or like the top 10 right singular vectors. All right, I want to get 2 to 10 dimensions, which so now I want k equals 2 or 10, or even if I want to do like 50, this might still make sense to do, depending on how accurate I want to do. Okay, and so I'm going to have a parameter. Now I'm going to have some approximation. Now I need some approximation. And I'm going to have a parameter kind of L, which is going to be either this is going to be 1 over epsilon, which will be an error parameter, which I'll explain what it means, or it'll be what is it, k plus, or it'll be k plus 1 over epsilon, depending on what sort of guarantee I have. Okay, so I'll tell you the algorithm, then I'll tell you the sort of guarantees you can get with this algorithm. Okay, and so this is an algorithm that's called frequent directions. And so I like this one because I helped with kind of so some of the first analysis of this algorithm, or a little bit refined analysis. And we're gonna start by initializing a matrix B in, this is going to be, we'll call this L by D. Okay, so it's going to be an L by D matrix. So this will be our space. So our space will be L times D. If D is like 10,000 or 100,000 and L is 10, this is a huge reduction in space. I'll be storing on the order of 10 or 20 kind of rows instead of like 10,000 rows. Okay. And so now I want to, okay, and I'm going to maintain this matrix B. Be a matrix B. It's going to have D here, and this will be L. Okay, and I'm going to maintain that this bottom row is going to be all zeros. Okay, and at some point I will temporarily put something in this all zeros bottom row of this L by D matrix. And at that point, say, I need to clean stuff up. Okay, so I'll have an invariant. I will keep inserting. And in fact, a bunch of the other rows, I may have other rows be 0, but every time I have, the last row is filled up with some non-zero stuff, then I need to clean up and shrink this. Okay. Okay, so now the algorithm is going to work. So I'm going to now, for AI for such that I equals 1 to n, right? Or so I'm going to go through the rows, 1 through n rows. And so I'm going to have a bit more complicated here. So first I'm going to say if the, so I'm going to, yeah. So the first thing, I'm going to insert AI into empty row of B. Okay, so if the all zeros row, if the last row is always all zeros, I can always do this. If there's another all zeros row, like I just initialized, I can put it in a different one of those spots. Okay. Then I have a condition, if no all zero row, then I need to clean stuff up. Okay, so now I have another if condition I have to deal with. At this point, I'm going to take the SVD of B, okay? The SVD of B is L times D, so I can do this in D times L squared time. So it's not too bad. It's a little bit painful, but I kind of sometimes will have to do this. Okay. I'm gonna let delta equals the sigma L squared, the squared value of the last singular value. So the squared value of the last singular value. And then kind of the tricky step is I'm going to set S prime equals to the diagonal matrix basically of sigma 1 minus squared minus delta square root sigma 1 2 squared minus delta square root sigma 3 squared minus delta square root and so on. So I'm going to take all the singular values of S, which I got out of the SVD, and I'm going to shrink the squared singular values by the smallest squared singular value. Okay. Then I will multiply B. I'm going to get B back. B is now going to be S prime times V transpose. Okay, I've run out of space, but good because the algorithm is done. Okay, I'm maintaining B, I return B at the end of the algorithm. Okay, so this is the end of the algorithm here. Okay, I have to return after this, then return B, right? Returns the actual matrix that I'm maintaining. Okay, so what have I done? If there's an empty spot in the matrix B I'm maintaining, I add the row. If it gets full, I do SVD and I say, I need to somehow shrink the matrix a little bit in all the directions of the SVD. Does this remind you of any algorithm we talked about earlier in the semester? Another streaming algorithm where if all of our counters were full, we had to shrink all of our counters. Remember the Misha-Gries algorithm? So it's really doing the Misha-Gries algorithm on the matrix. It has the property that if you do the SVD, it decomposes it into an orthogonal basis. And by the Pythagorean theorem, I can shrink all of the squared singular values and not really mess anything up. It kind of works if you shrink along, if it's completely full, I have all my counters are full, I shrink everything, and the last row now becomes empty here. When I do this at the end, S prime, the last term here, the last term needs to be is 0. And so this ensures that the last row is empty because I've done the sigma L squared is equal to delta, so that I subtracted the last term is always 0. And so afterwards, the last row is 0. And again, I can insert one more thing in. Yeah. So I have the invariant at the end here that the last row is 0. Now, if you notice, I can recover B with S prime by doing U, S, V transpose, multiplying those together. I don't multiply by U. I don't need the U matrix. Okay, the U matrix is just a change of basis, but I really want to keep that 0 there in the last row, I need to stay in kind of the right singular vector basis. If I rotated it, the last row won't be 0. Okay. Okay, so there's one more trick you need to think about here. Actually, this algorithm is actually kind of slow because I only free up the last row here. Okay, so there's a trick to speed this up with a little bit more space. Instead, I do 2L rows. Okay, and I'm going to maintain now that the invariance is changing a little bit here in that this last row is going to be empty, but I still keep, even with this change, I'm still setting this equal to the last value here, to the sigma L squared. And so now afterwards, I set L of these entries to 0. So I've doubled the amount of space, but I only hit the if condition every L steps. Okay, so now I need to call an SVD, but I don't call it every time I see a new thing. I only call it every L steps. So now the runtime is going to be O of N divided by L. Okay, because every N divided by L steps, I call this times 2L squared, or 2L squared times D. This is the call of this is the SVD time. And so overall, this equals to O. One of the 2 is a constant factor that becomes 4, but one of the L's cancel out. So now it's L times D, N times D times L. Right, so this is the runtime. So I've reduced the runtime from ND squared, which is been ND times 10,000, to ND times 10, roughly, maybe to ND times 40 if I have an extra, this 2 squared in front. Okay, but I've reduced the runtime significantly if I have if I start with a quite high dimension here. And this overall space is pretty small. Okay, so this gets a pretty strong this is the deterministic algorithm. It's kind of the best possible you can do for certain space bounds and almost the runtime bounds. There are some very, very high dimensions. You can improve some dependence on N and D through, you first do random projections and some stuff, but you have to be super high dimensions to really improve upon this. Okay, let me tell you about, so this does not give me the optimal SVD anymore, right? The sum covariance matrix, I exactly got back to SVD up to numerical errors, right? In this case, I've done some approximation. If you might thinking, why don't I just delete the last row every time it fills up? It's called a truncated SVD, and that sometimes works, but you can fool that. And there are some cases where that has a catastrophic fit. And even on some real data sets occasionally. And this one can avoid the catastrophic failures, and you can get it to be kind of basically as fast and not much less error. Let me state a little bit more carefully. There are 2 error guarantees. So I can either set, so I can have 2 claims. I use a frequent directions on A to get a matrix B. That is, and so B is in L by D. And so I'll just use the version with L rows instead of 2L. The error guarantees are the same, just the 2L rows just improves the runtime. Can I have 2 approximations? The first one is I can say for all X in our, and we'll talk through kind of what these mean. Write this up. Okay, so what does this say? It says for all directions X, think of it as a unit vector, but if it's not, yeah, so this is, I think we say X is equal to 1. For any direction, I can multiply I can look at the direction in A and look at the direction in B, and the direction in B is always going to be smaller. So I've always shrunk the matrix like the Misha-Green sketch. And the bound is determined by the tail of some K so I want L to be bigger than K so that I take the tail and so I think about so if you make L twice as big as K that you want, if you want it You want 10 dimensions, you make L 20. And so then you're dividing by 10. And so I look at all the mass that's in the tail, the part that's not in the top case singular values. And if that is small, then my error is small. And I can drive it down by making L kind of larger. So if you set L equals to in this bound to K over epsilon plus K, then this is 1 plus epsilon A minus AK. Okay, and this is in some sense you can't do better than this. I want it to be as close to the tail as possible. It's kind of a weird thing where I'm measuring the difference in a direction versus everything in the tail and the Frobenius form of the tail, but this is the bound you can write down. The second version is you can write down A minus, and now I'm going to project onto the rank K version of B, which could be less than the rank L version. I'm going to do a projection onto that of the matrix A, right? So if I were to go back and project onto this with another pass over the data, then this is going to be less than L minus L over K. Actually, this bound, wrote the wrong bound. This one is K plus 1 over epsilon. Okay, and this bound gives me A minus AK. Okay, so here, and then in this case, if I set L equals to K plus K over epsilon, then I will get that this is less than or equal to 1 plus epsilon A minus AK. Okay, so this is saying that this is the best rank K approximation, right? And I can get within 1 plus epsilon. So I'm projecting onto a K-dimensional space. Okay, I'm finding the best rank K I found from B. I project onto that. If I set L equals slightly bigger than K, okay, then I can get a good approximation of the best rank K space if I go and project on that instead. Okay, so I'm not getting exactly the best rank K approximation or the best 2 approximation, think of that, but I'm getting pretty close to it. And I can get arbitrarily close as I set L to be larger. Okay, all right, so don't want to dwell on this too much, but I do want to say, so this, if your goal is dimensionality reduction, these are useful sort of error bounds. I want the direction in any subset to be preserved. If there are directions that are in where if AX is very small, I can round it down to 0. And I get a good low rank approximation. But if I want to use this matrix for doing regression, let's say I want to learn a regression or a classification problem is slightly different, but if I want to do a regression problem on my sketch matrix, these bounds don't help very much. This doesn't say anything about regression here. I need a stronger guarantee for regression. Turns out if you want to do ridge regression, you can make this work. Okay, but if you want to do kind of regular regression, then this does not give you the sort of strong error bounds that you want. Okay, so for regression, you instead want something like a relative error bound. You want 1 minus epsilon to be less than or equal to AX um, 1 plus epsilon. Okay, I kind of want a relative error here to get regression to work because I don't know with regression, I'm going to learn basically a direction in the d-dimensional space, which I'll project onto, and that this value along there will predict my scalar value. And so I don't know if that's going to be in the null space of the top K or not. If I want to do principal component regression, I could do this. I could use the frequent direction bound, or it turns out ridge regression. But if I want to do regular regression, I need a bound like this, which is a little bit stronger. Okay, this is not, so this does not hold for frequent directions. Okay, we'll see another approach soon where this sort of bound holds for. And then you can do dimensionality reduction and then run a regression algorithm. And some of the fastest ways to run regression algorithms to get approximately optimal solution goes through one of these other techniques. But if you just want to do kind of a fast, maybe 2 or 3 digit of precision dimensionality reduction or SVD, then this approach is kind of the best you can do. Okay. Okay. Okay, I want to talk about another setting now. We're kind of flying through these, but I hope the algorithms so far have been pretty simple, right? The summed covariance, you're just adding up the covariance values. Seems pretty clear. This one's a little trickier. You're kind of iteratively calling the SVD and doing a little shrinking of each step. Think of it, if I just truncated the SVD, it would just be to set this to 0, but I'm doing a small variation on that, and that's maintaining small space. Okay. The next algorithm will be the setting when I want 2 things. Okay, so I have sparsity, and I want to I want to maintain. So I have sparsity in A, and I want to sketch it with the matrix B. By sparsity, I mean something like, 99.9% of all entries are going to be zeros. Okay, this happens in a lot of recommendation data. If you think of Netflix, all the movies that are out there and all the movies people are watched, they can recommend them based on if you have watched the movie, how long did you watch it? Or used to be, did you give a rating to a movie? Right? But most people have not watched most movies. So these are very sparse. On the products on Amazon, maybe some people buy a lot of stuff in Amazon, but they don't buy nearly all the products on there. So if you want to build a recommendation based on what you bought to some other product, that's going to be a very sparse actual amount of data. And so I want to maintain something that works as a low rank approximation for B, but I want to make sure I want it still to be sparse because, okay, the real size of it is not n times d. Okay, the size is not equals to n times d. Rather, it's what's called nz of A, which is the number of zeros, and this is often dramatically less than n times d. Okay, so I want B to kind of reflect the number of non-zeros in A. I don't want it to be bigger than n and z, and I don't want an intermediate representation that has a lot of kind of that becomes very dense, starting from a very sparse representation. Okay, so this is one property. The second property is I want to maintain example rows. Okay, you could think of this with column. Often this setting is called column sampling, and they transpose the matrix, and they think that the number of columns is bigger than the number of rows. We're going to call it row sampling instead. So I want to maintain example rows. And so I don't want to kind of think of what the result of SVD or of frequent directions is giving you these right singular vectors, which are linear combinations of all the directions. They're not really individually interpretable. Okay, so I want things I can individually interpretate what they mean, and then to look at the subspace defined by those things. Okay, so these are kind of the 2 properties I want now, and I'm also going to have n and d are going to be quite large here. Okay. And so basically, I'm going to sample, we'll call it L rows from A, and I'm going to put as rows of B. Okay, so I'm going to put these as the rows of B. Okay, so the question is, how do I sample the rows of A? Okay, so if I have a streaming algorithm, I can run reservoir sample, right? I'm seeing the rows one at a time, and I can just maintain a random sample of these L random samples. So can I just use reservoir sampling here? And the answer is not quite. This is not, I don't want this to be a uniform sample. Okay, so instead I need to do a weighted version of reservoir sampling. Okay, and this is a little bit trickier. I can do L independent weighted reservoir samples where I maintain a sample of size 1, but maintaining L things in a joint distribution with weights is a little bit trickier. There's ways how to do it, but I won't. Actually, I think they're described in the textbook in some of the earlier chapters, but we won't talk about them today. They're pretty cool algorithms. The real important idea here is I don't want to sample just any row. Some rows are more important than others, and I want to sample some rows more importantly. Okay, and so I want to put a row weight WI, and so the simple version is just called norm sampling, and I just do the squared Frobenius norm of the row. So I want to sample proportional to this weight. The larger the squared Frobenius, or the squared norm, it's not Frobenius norm, the squared norm of the row, the sum of the squared entries, the more likely I am to keep it. Okay, so I keep a running total of all the summed weights. I see a new score that has this squared weight, and I sample with this weight divided by the sum of all the weights so far, including this one. That's what probably I keep it. Otherwise, I kept what I had before. So I can maintain one of these samples. I do L of these independently. So I might sample the same row twice. Okay. Again, there are simple ways to fix this using called priority sampling. But I won't go into that in today's lecture. Okay, this is not the optimal way to sample the weights. This is a simple way that works pretty well. And sometimes in some cases, this works as well as the optimal way, which I'll tell you next. But this will get a bound. This way of doing sampling will guarantee this sort of property that A minus the projection onto B of A. Okay, this is not the low rank version of B. This is the full large version of B, which is going to be much larger than K that I actually want. The Frobenius norm of this will be less than or equal to A minus AK. Frobenius norm plus epsilon times A. So instead of relative error with respect to just the tail, the error is on the full Frobenius norm. Okay, so if the full Frobenius norm is much bigger than the tail I want, then my error is kind of bigger. Okay, but and this works with, and I can get this error bound with this is using L equals 1 over epsilon squared times, yeah, it's roughly K over epsilon squared. There's some probabilistic term here, so it's some constant probability, right? So K over epsilon squared instead of roughly K over epsilon. So I get an extra, if I want to go from 1% error, I have to get an extra factor 100 rows in the sample. Okay, so it's a weaker bound, but I get these properties. I maintain sparsity if it has a very small number of non-zeros. So the space is a big win, and it maintains actual example rows that have a good kind of span here. Okay, there's a better way of sampling. Okay, better row sampling with the leverage scores. Okay, and the leverage scores are, I think it's worth talking about them anyways, because they're an interesting concept. But let me just tell you what they are mechanically, and then I'll kind of talk a little bit about also why they're interesting. Okay, so if I want, so if I have A and I call the SVD to get U S V transpose, and I want the leverage score of AI, it's going to be U sub K, the ith row of this. Okay, so again, I'm going to get U S V transpose. Okay, and then basically this, I'm going to set all these to be 0 here, so that all of this stuff is 0, and this is the top K, right? This is the Kth term here, so these are K terms here. Okay, so now this value here, this is U sub K, and now I want the ith entry, so this entry here. So it's going to be the, I think it's the squared norm of this. So I just look at, so if I looked at the, so it's saying, let's look at the, what this is telling me is I'm looking at the, a representative in a k-dimensional space of the ith object. And this is the k-dimensional space that captures the overall kind of the overall the best rank K approximation of the data. This is in fact a coordinate in this space. Okay, this is before I've done the scaling. I'm saying how much does this term capture the coordinate in this space? Okay, and so what I know about this matrix, if I remember, is that this here, every column here, right? This column, the column has a squared norm of 1, right? It's a unit vector. Okay, so that means that if there's a dimension where there's only one data point that has a very large norm in that dimension, then that point is very important in the space. But if I have a lot of points that are important in this direction, then kind of the squared norm of that column is spread out over a lot of points. Okay, so if there's a point that has a large kth leverage score, it's important in that subspace and that it's representative. And if I don't sample that one, there aren't a lot of other good replacements. If it has a small score, it might be really well aligned in that subspace, but there could be a lot of other replacements for it. Okay, so it's kind of doing two things at once. How well is its mass in the proper k-dimensional subspace? So how well is it aligned with it? And how unique is it? If there are a lot of other copies that could be replacements, the score goes down. So think of this like the k-means plus idea, where I'm trying to sample some point from a cluster that's far away from everything I've done before, and I'll sample something from the cluster if it has a lot of points and it's far away. Okay, this is kind of scaling like this. So if there are a lot of replacement points for some ith term, then I don't necessarily need to sample from it, but I'll sample one of those points probably. If there aren't a lot of replacement points, then I will very likely sample this point. Okay, so I want to sample with respect to this leverage score. Okay, so this is, if I sample if we sample L equals, what is it, something, I think this is again K over epsilon squared points by or proportional to the leverage scores of these AI, okay? Then I'm going to have the property that A minus AK Frobenius squared is less or equal to 1 plus epsilon A minus AK. Okay, so then I can get the relative error here. Oh, actually, this was not. Okay, here, this is projection onto B of A. Right, so the subspace I captured from B is a 1 plus epsilon approximation. Okay, but I need to sample from these leverage scores. Okay. And this leverage score kind of is a good thing to think about, like if you have collinearity between data, right? Or if you're making this, you can make guarantees about this for, I think you can get guarantees on about regression with this as well. I don't necessarily need to get whatever is the causal variable or the causal row. I just need to get something that is well aligned with the causal rows, right? So you can make a good regression prediction or a good prediction on something without the actual causal variables, right? So there's some people, and I have some friends who've written some, well revered papers on this. They claim you get some interpretability out of here, because I want to maintain example rows. The ones that I've selected, if they give me a good basis for something, that maybe that says, well, these are meaningful towards the conclusion. And I don't think you can actually claim that, right? You can't actually claim that from here, because there might be another row that has a similar meaning, and that's the one that's actually meaningful. The one that you've sampled is just really well correlated with that. Okay. Yeah, the leverage scores also tell you something about, like, if a point is by itself has a really large leverage score, maybe you're sampling because it's an outlier point, right? That's another reason, another way to think about the leverage score. If it's super high, for even if you look at just, I can do this without a value K, right? If I look at the whole, I don't have any guarantee that the whole row is of norm 1. So if our leverage score for a particular, for the whole matrix is large, and that is very different from everything else. And that's what that point says. So any point that's in the distribution will have a low leverage score. Okay, so these are kind of interesting things to think about, and this is kind of the optimal way to do sampling. Okay, again, we're kind of flying through this. Okay, one more algorithm I'm going to talk about. And this is going back to like random projections. Okay. Actually, maybe 2 more algorithms. I want to now have a matrix B, which is S times A. And so I predefine S, which is going to be in L times N. Okay, and I can initially, I'm going to set so that every ij is IID normal 0, 1 divided by, what is it? Or times N times L. Okay, so I'm doing a random projection. Remember, we talked about that Monday last week. Doing a random projection from A onto B. Except now I'm not going from high dimensions to low dimensions. Remember, A here is going to be N by D. The matrix S needs to be N by L, and I'm going to get a matrix B at the end which is going to be, let me make this one a little bit skinnier. This will be L times D. Actually, I should make it longer here. We'll see why in a minute. Okay. Okay, so I'm going to make this each entry in here each entry in here, this will be kind of ID random variable scaled, again, scaled by n over L. So I'm projecting onto a space, and the idea is that I want L to be much less than n. Okay, so the dimension is the same here. The dimension is the same, but the number of rows is much smaller. Okay, so the number of rows is much smaller, so I'm reducing the number of rows. So I'm going from the n-dimensional space down to an L-dimensional space. So I'm not reducing the dimensions, I'm reducing the rows by random projection. Okay, and so my goal is to do something that is small space with respect to, and I don't need to store this matrix. For every row, I get a new row of this matrix S, so I can generate this as an algorithm, but I can kind of analyze it as if it was a matrix. Okay, and so if this is my matrix B, this is the case where I can get AX divided by BX. And so then I can run regression on the output here. So I can reduce the number of rows dramatically. So this is useful if, again, the number of rows is like hundreds of millions, and I want to run a regression algorithm on this. Okay, and so the new versions of like LAPACK, I've heard like Jack Dungara is actually involved in the rewriting of this, is using variants of these algorithms we've talked about, including this one. For very, very large scale matrices, actually doing this first and then running some stuff on top of it can actually works better at these very, very large scales. Okay, so I can generate the random for every row I process here, AI, it corresponds with a column SI here, and I can kind of generate this projection on the fly. Okay, this is not quite what they use. This is actually too slow because the S matrix is going to be too dense. Okay, and I have to create an L-dimensional, I'm multiplying A by an L-dimensional kind of vector, and it's affecting all of the entries of B as the output. Okay, what what you want to do instead is kind of a sparse version of this, where I'm going to have in here, I'm going to make S sparse. Okay, and there's a lot of questions like, could we do a random projection so it's sparse? And you can't do that in general here, but you can do something like a count sketch. So each column of S will have one non-zero, and that entry Sij is going to be -1 or +1 at random. Okay, so what this is doing is this is exactly like a count sketch. Not the count min sketch, but the count sketch, which is the frequency approximation idea, where I hashed every item into a bin, and each row now is like the item. And instead of adding it to exactly one thing, I'm adding or subtracting at random. If I had this right, yeah. So every entry AI is going to basically be hashed into one of the L rows of B. There are N of them, and kind of the analysis works that, again, if there are going to be some directions which are heavy, and I'm going to capture the heavy directions, and everything else is going to be approximately zero. So I can get this bound, I can still get this bound with the random projection. With this bound, I can set L equals to D over epsilon squared. With the count sketch, I need D squared over epsilon squared, but I'm going to maintain the sparsity. But I have sparsity, and so the runtime is basically going to be the number of non-zeros of A times 1 over epsilon squared. So I'm getting a much faster runtime, and so this count sketch version is like very fast. Basically, what's happening is every row, I'm reading it, I'm picking a random location in here, kind of the random value that is non-zero in this entry is telling me which row in the sketch B to put it in, and I randomly add it or subtract it. So it's as fast as reading over the matrix. I think it's like plus this here. I don't have the exact thing written down here. Okay, but this algorithm is extremely fast. It's really as fast as reading over the data. But the size of the sketch you get at the end is still quite big. Okay, so the number of rows here is something like D squared. Okay, so I'm hashing into a large number of rows, and then I need to clean this up afterwards. So maybe you could then pass this thing, if you think it's still too big, into frequent directions or into another SVD algorithm to kind of clean this thing up, because the number of columns is still going to be quite big. Might be, this works when the dimension you're mapping down to is like 500 or 1,000, but it works very fast. And then you can run regression on that. And if that's much better than 100 million, then you've won. Okay, but if you're trying to map this down into 10 dimensions or to 2 dimensions, it's going to give you some nonsense. Okay, so these are extremely large scale algorithms, but this is the scale that is sometimes comes up in these very large scale kind of machine learning and recommendation systems. Okay, I think I got through what I wanted to get through, but I know I went pretty fast. So let's I'm sure people have some questions. Yeah.
Can I ask you to maybe write out this process?
Yeah. Right. Let's write out the count sketch algorithm. Okay, and so I'm gonna initialize B, which is going to be in L times D, where L is going to be something like O of D squared epsilon squared. Okay, and then I'm going to for AI, for I equals 1 to N. Okay, now basically how this will work is I'm going to choose J in uniform between 1 and L. Okay, so I'm going to pick an index, 1 of L, and then I'm going to choose SI from uniform of -1 plus 1. And then I'm going to set B J. This is the jth row of B. It's going to be BJ plus SI, which is a -1 or +1, times the row of AI. Okay. All right, so this is the algorithm, right? So very, very simple here, right? So at the end, I'm going to return B. Okay. Now the idea is that the column information of B is going to be captured up to a sign, right? Some things I've added or subtracted on top of each other, randomly combine these things together. But what I care about, remember the guarantee is something like for all x, 1 minus epsilon less or equal to ax squared divided by bx norm 1 plus epsilon. Right, so how I'm querying this is I have a vector x, and if I multiply it by b, this is a d-dimensional thing, then it should, this norm, I'm taking the component along for each jth entry of x, I'm looking at the norm in the jth column of b. And so if I get the sign wrong, well, I'm taking that and I'm squaring it and adding these up. So the sign doesn't matter inside of the norm, right? So bx is going to be equal to the sum of j equals 1 to d of, what is it, of bj dot x squared square root. So if I get the sign wrong in the bj, right, it's not going to matter because I'm dotting it and then and the sign factors out and then I square it, right? So I could get the sign wrong here, but that's not going to matter when I'm evaluating it with just the direction and some. And so what's great here, right? So if all I'm doing, right, look, the key step is this one here that the other, you can speed up the randomness with some pseudo randomness if you really care about it. But this is the key step. I'm basically taking a kind of a d-dimensional row and I'm adding a d-dimensional or subtracting a d-dimensional row to it, right? And so if this row AI is sparse already, it's almost all non-zeros, I only have to find the non-zero entries and add or subtract them from what's here. Okay, so for really sparse things, it's very fast. I only have to read over the non-zeros. To get this to work, you may want to actually repeat this something like log 1/delta times to get a better estimate of this guarantee. But it works okay even without doing that if your dimension is high, right? If the dimension is high enough, it's basically these things are going to act like a hash table, and you're going to have very few collisions, right? And so basically what happens is there are only going to be so many. If there are only so many important things, you're going to preserve all of those, and the other things will kind of cancel out pretty much on average. Yeah, okay, cool, great. So this was a lot of material covered today. Hopefully you take away the big picture of how to run these things at scale. I would start at the sum covariance. If this doesn't work, or if your algorithm, because this will be a small space efficient algorithm. The frequent direction would be the next biggest thing. And if you really want the kind of sparsity or the column interpretability, you can try column sampling. It's pretty easy. This one, you could try if it gets that super, super big scale. And I know people who've implemented this inside of some companies, and this is how they process very, very large scale data. But it's a bit more kind of making sure you have the right kind of scale here is maybe a bit tricky. All right, we'll stop here.